All right, I've talked about several resistivity tools already. I'm going to talk about one more, which is very different from the others. I've kept it separate because although it's called a resistivity tool, it is entirely different in the way it operates. It's a resistivity imaging sensor designed to image the inside of the borehole, and the only thing it really has in common with those other tools is the fact that it is a resistivity-based measurement. The tool in question is the AFR, the Azimuthal Focused Resistivity tool. The main function of this tool is as a borehole imager, providing very high resolution images of the borehole like the one shown on the screen. If you notice the depth scale here, this is only 5 feet between depth markers. You get a sense of the high resolution of the measurement that this tool can provide compared with some of our other tools. Just to give you a sense of scale, this is something like 10 times better resolution than any other measurement that's available on LWD at the moment. So why do we bother with imaging the borehole? This is an image of the borehole that's based on a resistivity measurement, but why do we do it? What are the main advantages? The main thing is it gives us the ability to visualize the reservoir structure that we're drilling through. Conventional logs gives you some idea about the formations, but an image like this gives you way more detail and allows you to visualize the structure much more clearly and as I said, in more detail than we can with other measurements. The interpretation of the image data allows us to calculate formation dip, so the angle that the bedding planes are angled relative to the horizontal or relative to north. Measurement of dip, of course, is important if we want to understand the shape of a reservoir structure that we're drilling through. It also has enough resolution that it can identify fractures in the rocks and allow you to measure the orientation and location of those fractures. Again, that can be very important for rock strength interpretation or understanding stress orientations in the rocks. The fractures will help you to make interpretations of those things from the image data. Fault planes also show up. There's actually an example in the picture that I'm showing here. There's a fault right in this area surrounded by a swarm of fractures and little microfaults, which makes for a very complicated view, but also contains a lot of valuable information in that image. In the hands of an analyst, you can extract a lot of detailed geological information about what's going on around that area. We can differentiate between lithologies. When I say that, I mean differentiate between them simply by the way they look on a log. You can obviously use conventional logs to differentiate between lithologies, but with imaging, it's a much more qualitative thing. You can just look at an image and recognize formations simply by their texture or their color or other aspects of them, which is very useful in some situations where, for example, if we are in horizontal wells or wells which are moving up and down through a sequence, we may pass through the same bed multiple times in an undulating horizontal well. And being able to recognize particular formations from their appearance on an image can be a very useful tool. In real time, we can use those images for geosteering decisions, especially if we're trying to steer through thinly laminated formations where the deeper reading tool like the ADR gets confused by the laminations and can't fully resolve all the different beds that are around the borehole. Using a real-time image gives you very fine control over the geosteering job and allows you to steer relative to those thin beds quite accurately. Another advantage that we have in LWD over the wireline, of course wireline tools produce borehole images similar to this, is that we get in there very early. We're in the borehole early on. We're in there as it's drilled, when it's at its freshest. There's been very little time for invasion or borehole washout to occur, so it means the borehole is in its best condition for image logging. When we go in later with the wireline, there's a risk that the borehole could have degraded to the point that it's not possible anymore to get reliable image data. And the other benefit that we have over wireline is the 360-degree coverage. You can see from the example that we have complete coverage from the top side to the bottom side and back to the top, all the way around the borehole, which in general doesn't happen with wireline. With wireline, the tools that are run have pads on them which only cover a portion of the borehole. We take advantage of the fact that LWD tools rotate to allow the tool to scan the entire borehole, producing a complete 360-degree image. Now I'll just give you a quick overview of how the tool works. This is very different from the way that the other tools work with the wave propagation technology. This tool is very different, and I'll just explain exactly the mechanism that is used. What we have is the tool collar, shown in grey here, and around that we have a toroid, which is a ferrous ring of material, and wrapped around the toroid we have a coil of wire through which we pass an alternating current. When we do that, what we get is an alternating magnetic field inside the ferrous core, and in the same way that an electrical transformer works, that then results in a current being generated in the collar itself. Now the picture shows just a single direction. You have to remember this is actually alternating, so it's an alternating current in the windings, an alternating field in the core, and an alternating current flowing in the collar. But for most applications you can just think of it as being DC, direct current, which makes things easier to visualize. And the key point here is that we're generating a current in the collar without actually having any kind of direct electrical connection to the collar. It's all done by induction in the same way, as I said, that a electrical transformer works. So this diagram shows the toroid on the tool that's generating current flowing down the tool. Now the tool, of course, is in a conductive environment. It's in a water-based mud, a conductive mud, and the formation around the tool is also conductive, which means that the current doesn't stay in the tool collar. It will radiate out through the mud in all directions and into the formation. And eventually the current will find a way back to the other side of the transmitter to make a complete current loop. Now the thing we're interested in is the tiny piece of that current that's flowing out through this little green measurement electrode. If you look over on the right here, we've got a zoomed in version of that, where you've got the collar and the green button electrode. The button electrode is electrically isolated from the collar at the sides. The only place where current can flow is through the stem of the button, which is right here. And wrapped around the stem we have a little tiny toroid. It's very similar to the transmitter, except it's working in reverse. We push a current through the middle of it. That generates a voltage in the coils around the toroid, which generates a small current in the measurement electronics. So we can measure the current that's flowing through this button without actually interfering with it. Now where does that get us, is the question. Well, what we then use is a version of Ohm's law to calculate the resistivity of the formation, because the amount of current that flows out through this button is going to change depending on the resistivity of the formation that's immediately in front of it. And it's that resistivity that we're really looking for. So we measure the voltage, we measure the current, and then we can put those two things into this equation down here, where the resistivity of the formation is a function of the voltage, the current, and a geometric factor which takes care of the size and shape of the tool and the button and so on. This picture shows you what the tool itself actually looks like. We've got stabilizers at each end of the tool. These stabilizers are just slightly smaller than the borehole, and they're there to keep the tool centralized in the borehole and to minimize the amount of wear that we get on these pads which carry the measurement electrodes. Next to the stabilizers you have these covers which conceal the toroidal transmitters. There's one here and there's one at the other end. By having two transmitters and a symmetrical arrangement of receivers or button electrodes in the middle, what that gives you is a compensated design. You remember I was talking about compensation for the other resistivity tools, the M5 and the ADR? Well, the AFR also uses compensation, although the actual mechanism that's being used is different. The same concept applies, that you can make a measurement from one side and a measurement from the other side, combine the two, and that helps to reduce the errors which exist in the measurement, making for a more stable measurement. And it also reduces the effect of boundaries where you might get some distortion. The compensation tends to reduce the amount of distortion you see at boundaries. In between the transmitters you have an array of button receivers. Each button is mounted on a pad. The four circles that you see are actually just the bolts that hold the pad in place. The measurement electrode is the thing in the middle. We have a small button on this pad, a small button on this pad, and a larger button on the one in the middle. I'll explain why that is the case in a minute. Each row of buttons has three buttons in it. So this, you're just seeing one side of the tool. There's another pad around the other side and another pad down here. They're 120 degrees apart around the tool. So there are three buttons on this row, three buttons on this row, and three buttons on this row, giving you 9 buttons in total. Now, there are two different sizes of button electrode on the tool. We have what we call standard resolution buttons, which are about 1 inch in diameter, and high resolution buttons, which are about 1/2 inch in diameter. Those are mounted on different rows on the tool. So generally speaking, you'll find that the top row will be equipped with high resolution buttons, the middle row will have standard resolution buttons, and the bottom row will have high resolution buttons. So the question then is, why do we bother with two different sizes? You would think that we would just go with high resolution buttons and that would be enough. Well, the problem is that they each have advantages and disadvantages, and the high resolution button on its own would limit what we can do. The reason being that because it has such a small surface area, when you bring that in front of a formation which has a very high resistivity, the current that's flowing out through that button gets very small and it becomes very difficult to measure. In fact, so difficult that it gets lost in the noise of the electronics of the tool, and the resulting resistivity measurement gets extremely noisy. That happens at about 500 ohm meters or thereabouts, formation resistivity. So to maintain a measurement above that, we keep the standard resolution buttons on the tool. Because they have a larger surface area, that means that there's more current flowing through them. The current flow is actually proportional to the surface area of the button. So this one is about 4 times the surface area of this one. So when we get into a high resistivity formation, this current stays higher than the current flowing through the high-res button, which means it's still measurable above the noise of the electronics. So that allows us to make a measurement in formations all the way up to 20,000 ohm meters, even though the resolution of the image that we get from these buttons won't be quite so good. In practice, we can usually see most of the features that we're interested in with the standard resolution button, just not with the clarity that we can from the high resolution button. Of course, being an LWD tool, we have to provide different sizes of this tool to suit different hole sizes. We have 3 sizes. We have a 4 3/4 inch tool, a 6 3/4 inch, and an 8 inch tool. The 4 3/4 and the 6 3/4 are laid out in much the same way as I've already described, with 3 rows of buttons, with the transmitters either side and the stabilizers either side of that. The 8 inch tool is a little bit different. It has the 2 stabilizers, but this time the button electrodes are mounted directly in the stabilizer blade rather than being in between the two. And it only has 2 rows of buttons rather than the 3 rows which the other 2 tools have. However, the bottom row here is mounted, is fitted with what we call a dual resolution button. What that has on it is a high resolution portion, which is the central portion of the button, and that's surrounded by a larger area which acts as a standard resolution button. So we've effectively got a high resolution and standard resolution at the same place on the tool. So you can think of this lower row as effectively having 6 buttons, 3 high resolution and 3 standard resolution. Meanwhile, the upper row here has all standard resolution buttons. So a slightly different configuration, but when it comes to the logs, the data that they produce is comparable to what we get from the other 2 tool sizes. So I'll just take a moment to explain how we generate an image from the data that this tool generates. In principle, the generation of an image is the same whether we're talking about a resistivity tool, a gamma ray tool, or a density tool. The logic and the principles are all the same. The only difference is the physics of the individual measurements. So I'll explain how the AFR works, and then you can apply the same logic to the other tools that we'll talk about later on. What I've got here is a cross-section of the borehole. The tool, as you can see, has the 3 buttons on it. I've colored them red, green, and blue. And just for the sake of illustration, I've divided up the borehole into 16 azimuthal sectors. Ordinarily, with AFR, we would use at least 32, maybe 64 sectors, sometimes as many as 128 sectors. That's difficult to draw, so for the purposes of illustration, we'll just stick to 16. And the binning, the way these bins are drawn, the high side of the hole is the divided is the line between bins 1 and 16. So this is the high side of the hole right here. If we were using magnetically binned data, that is reference to north, we do that sometimes, then north would be on this line instead of high side. So this would be the north reference right here. But let's assume for this example that this is the high side of the hole, and that we're looking down hole in this image. So the bins are numbered clockwise, looking down hole, starting with number 1, just to the right of high side. Now this tool is spinning, it's rotating in the hole. So each of these buttons is passing through each of the bins as the tool rotates. And what we do is we measure the resistivity extremely rapidly, so very, very rapidly, every few milliseconds, we'll take a resistivity sample from each of these buttons so that we get samples in every bin from every button as the tool rotates around the borehole. And what we're going to do is plot the resistivity from those buttons and plot them versus the bin number that they fall into as the tool rotates. So to begin with, the tool might rotate a little way, and we get, say, the red button gave us a number in value in bin number 9, the blue button gave us a value in bin number 14, and the green button in bin number 4. And as the tool rotates more, it continues to fill up those bins with samples. And you'll notice that each bin can contain samples from all 3 buttons. And in practice, it may contain multiple samples from all 3 buttons, depending on how many times the tool rotates during a sample period. At the end of a sample period, we take an average of all the values that we've accumulated in each bin to just provide a single resistivity value for each bin. And that's what we can then take and plot as an image on the log. So let's see how that operates where we have some formation around the tool. Here we have the tool again, and this time we're in a low resistivity formation. We're in a horizontal well or near horizontal well, close to a boundary with a higher resistivity formation. And we're going to look and see how the resistivity values in these 16 bins, how they change as the borehole slowly penetrates the boundary. So there's the tool spinning, and we get a set of resistivity values in the low resistivity formation. As the tool cuts down through the boundary, some of the bins start to see the higher resistivity formation. As we cut down further, we see more and more of the bins exposed to the high resistivity, until finally all the bins now are exposed fully to the high resistivity bed as we've completely crossed the boundary. Then we take an average of the resistivities in the azimuthal bins, and we can assign color coding to those values. So we take this color scale from a low resistivity to high resistivity, from dark to light colors, and we can assign particular values to a particular color and then present that on a log. So the first line on our log here came from when we were still in the low resistivity formation. The next line comes from when we're partially crossing the boundary. The third line is where we're almost all the way across the boundary, and the fourth line is when we're fully across in the high resistivity formation. And on here, this is measured depth down the side, plotting versus the top of the borehole or the north side of the borehole, depending on what reference frame we're using. And you can see that what we've got is the beginning of a classical boundary shape. Typically, when we cross a boundary, we get something that looks like a sinusoidal shape. This is obviously very rough, but you get the idea that we start to see this gradual change as we move down the log. We can see the high resistivity formation appearing until it finally fills up the full width of the plot. Another way to help visualize what's going on is to think about how the image is actually generated and what it represents. What you can do is think of the borehole in this way, where we are drilling to the right. We're drilling along a borehole that's horizontal. We've got the top side here, the bottom side, the left and the right side of the borehole here. And we've got some feature. This could be a bedding plane, it could be a fracture, it could be any number of things that is crossing the borehole at an angle. And we take some measured distance along the borehole to go from one end of that feature to the other. When we present an image, what we do is we're effectively cutting the top side of the borehole along the dotted line as shown, and opening out the borehole and laying it out flat, so that you end up with this feature, which started off as an elliptical feature in the borehole, turns into a sinusoidal feature when it gets laid out flat. And on the right, we have the conventional way in which we view that. We don't normally look at it sideways, we normally look at it this way up, where this distance d is the same as the distance that we saw originally. So the height of the sinusoid that we see on the log plot represents the distance we had to travel along the borehole to get from one end of that feature to the other. You'll also notice that the order in which the top, the right, the bottom and the left appear is kind of counterintuitive. We have the top is at the edges, which is easy enough. The bottom is in the middle, which again is easy enough to understand. But the right and the left appear back to front. But if you follow this sequence through, you look at this for long enough, you'll be able to see how that works. That the right-hand side of the borehole actually shows up on the left-hand side of the image when we present it in this way. Now here's an example of some real data from the AFR tool, showing you the kind of thing that you can normally expect to see. At the bottom we've got a representation of the structure that we're drilling through. We've got a low resistivity formation shown in dark colors. You've got an intermediate layer and then a high resistivity layer above. The blue line is the TVD, the true vertical depth of the well, and the two black lines either side of it represent the actual diameter of the borehole. This is I think this is a 6-inch diameter borehole that we're in here. Above that, you've got the image that came from the AFR. So you can see that as we're cutting up through the structure here, we see the formation features appearing as sinusoidal shapes pointing to the right. As we change direction and come back down through the same structure, the direction of these features changes and they're kind of pointing to the left. Above that, by the way, we've also got 3 ring resistivities. These are resistivities which are basically the average resistivity from each row on the tool, providing a shallow, medium and deep, what you can think of as being a lateral log style resistivity measurement, similar to a wireline lateral log, although it's rather shallower than a wireline lateral log. And at the top we've got the at-bit resistivity. This is another measurement that comes from the AFR, which is a little different, and I'll talk about that later on. Anyway, so we've got this image. We don't normally look at it sideways, though. We normally look at it when it's vertical this way. And a useful way to remember how to interpret these sinusoidal features on the log, particularly when it's the middle of the night and you've been up a long time and you're trying to geosteer a well, is that if you see a feature that looks like a smile, that means that you're going up through the structure. And if you see one that looks like a frown, you're going down. That rhymes in English, but it doesn't work probably in any other language. But it's a useful reference to try to remember which way you're going when you're looking at images. You can remember that simple rule to help guide you through the structure as you're looking through an image. And sometimes these images can get quite complex. They're much more complex than this simple example. So it gets more challenging to remember where you are in the structure. Now, in the last slide, I mentioned the at-bit resistivity measurement. This is something which also comes from the AFR, but which really has nothing to do with the imaging or the ring resistivities. This is something which is used mostly for geo-stopping, that is, stopping drilling when the bit penetrates a particular boundary or maybe a reservoir contact or something like that. The way it works is that the lower transmitter on the tool acts as a receiver. It switches functions and acts as a receiver. The current driven down the tool by the upper transmitter, which is also driving the current for the imaging buttons, some of that current makes it as far as the lower transmitter and can be measured as that transmitter is now acting as a receiver. The current that's flowing through that point will also then flow out through the bit and through any other parts of the BHA which are below that point. What that effectively means is that from this point on the tool to the bit, the BHA acts as an electrode which can then be used to measure the resistivity of the formations immediately around that part of the BHA. So it's not a very focused measurement. This distance can be 30, 40, 50 feet, but it is good for detecting changes as the bit penetrates low resistivity formations, like, for example, drilling out of the reservoir into a water zone. The closer this receiver is to the bit, the sharper that measurement becomes, but in general it's a pretty lazy measurement, a pretty lazy response compared with the lateral log resistivity measurement and the image measurement. Now here's an example where we show both the high resolution and the standard resolution data. You remember I said we had two different sizes of button on this tool? Well, here's a log which shows the two side by side. These three images are the main thing I want you to look at. We have a high resolution image here on the left. This is raw data. This is what we call a static image. It hasn't been enhanced or changed in any way. This is just the data as it comes straight from the tool. But this is the high resolution button, so this is the best resolution that the tool provides. Next to that we have the same data, but it's been enhanced dynamically using Borehole Imaging Studio, which is an application I'll talk about in a little while. We take the data and we enhance the contrast so it maximizes the detail. We can see all the small details with as much contrast as possible in the log to bring out all these fine features. We've got thin beds here, and we've got a lot of fractures. These kind of U-shaped features are fractures in the borehole wall. And on the right, we've got the same interval logged using the standard resolution button. That's the 1-inch diameter button. You can see that we can still see most of the features that we can see on the high-res image, but we don't have the detail. We lose some of the detail, especially in the fractures down here, which you can see on the high-res image. Over on the left, we've got those ring resistivities again, which again are the average of each row. You can see that because the borehole is at an angle to the bedding planes, that the ring resistivities tend to smear out these thin features here. They're basically smearing out over a few feet, a feature which is actually only about maybe a few inches in thickness. So you need to be a little bit careful interpreting the curves from these ring resistivities. But the main thing to look at on this slide is the images and the differences between the standard resolution and the high resolution data. This is an example of what you might see in real time versus in memory from the AFR. On the right hand side here you've got a real-time image. This is from a very high angle well. We are parallel to the bedding in this interval. We move slightly relative to the bedding and then move up out of it. You'll see that the tail end of this looks like a smile, so we're moving up out of the structure into this high resistivity bed above. You compare that with the standard and the high resolution memory data. Obviously those have a lot more detail in them, especially the high resolution data. But for the purposes of real-time steering, the amount of information that you get in the real-time image is still enough. You can see how the well is moving through the structure, and you can make steering decisions, very fine steering decisions, based on that information. You can see here that we're looking at bedding planes which are very, very thin. This is the circumference of the borehole from left to right, which might be 18 inches or something in a 6-inch hole. So we're looking here at a bed which is an inch or two in thickness. In fact, there's 2 or 3 beds together which are all about the same thickness. So we're seeing a great deal of detail. In this case, we're traveling along a bedding plane and then just leaving it towards the bottom end. This is another example showing you the sorts of detail that you can typically see in an AFR image. I should point out the depth scale here. This is a 5-foot depth interval. So we're looking at some very fine features in this image. On the left, we've got the static image, and on the right, the dynamically enhanced image. So this is the same data. This one has just been enhanced. And we can see a few things. We can see the sinusoidal features crossing the image here. These sinusoids, these are bedding planes, sedimentary bedding planes. We also see these sort of chevron patterns, these V-shaped patterns, which are typical of drilling-induced fractures. Those are associated with the stress field in the rocks. As we drill through the rock, the stresses around the borehole change and result in fracturing in a particular direction, which tells you something about the orientation of the stress field in the rock. Also in the image you can see some very small features, these little dark spots. They could be a couple of things. They could be pyrite or something like that, some kind of conductive mineral. Remember that dark colors represent a low resistivity or a conductive material of some kind. Or they could be holes. They could be vugs, small cavities in the side of the borehole, which will be filled with the drilling fluid, which is typically very low resistivity, and that will show up as a dark color on the image. You can see that some of those are very small in size, on the order of half an inch or thereabouts, which shows you the kind of resolution that this tool is capable of. Something else I'll point out on here is these fractures. Here's a drilling-induced fracture going into a lower resistivity formation from a higher resistivity one. From this you might infer that the high resistivity formation is a harder rock, whereas this is slightly softer and is tending to fall out or break out or crumble. The fracture is enlarging in this slightly softer rock, whereas it's not enlarging in the harder rock. That's kind of the beginning of borehole breakout, probably. If we were to come back and log this interval later on, we might find that these fractures had got a lot larger and that some of this hole had enlarged significantly since we first logged it. Now, if you're an FRS analyst or interpreter, Borehole Imaging Studio is a piece of software that you will probably become familiar with, and AFR data is one of the main data sets that will be used in this software. This is a piece of software that's used to interpret the image data to identify, or to help you identify, all of the different formation features and borehole features that you can see in the image. So it contains multiple features. You can get all kinds of outputs from Imaging Studio, from detailed plots to fracture frequency identification plots, core box representations, So this is like as if it's almost like a pseudo core type view. Some statistics, you can get all kinds of fracture statistics and other statistics out of the software. Some interpretation of some complex zones, like around a fault. Here's an example where it's an extremely complex situation, but all the different features have been interpreted and classified to help you understand, or help the customer understand, what the structure is doing. And three-dimensional views of the wellbore even. Sometimes it's useful, rather than looking at a flat image, you can look at the data as if it rolled back up again into a borehole, so you can see more easily what the actual shape of the geological structure is through that interval of the borehole. That completes a summary of our resistivity sensors. We do have a lot more training available in those sensors, particularly on the geosteering and also on the imaging and image interpretation side, which you may get at a later date.